All right, back for one more example to finish up lesson 18, video 18D, still looking at modeling the sample mean. So first example, assessment records in Cecil County show that the mean home value on the books is $224,000 with a standard deviation of $65,000 and a very skewed right shape. Local officials decide to take a sample of 100 homes. This very skewed right shape, if you think about this, that should make a lot of sense, right? Most home values are down close to this average value of 224, but if you look around in the county, if you opened up the paper and looked at homes for sale, you'll find a couple, not many, but $1 million homes, $10 million homes, so that causes that tail to go out to the right. Okay. So fully describe the sampling distribution model for the sample mean, not for individual home values, the sample mean. Draw, label, and why can we use this particular model? Okay, so just from the previous bit of information, keep in mind that assessed values are skewed right for individual homes, right? But now we want to look at sample means. We said that we looked at a sample of 100 homes. What would the distribution of the sample mean look like? Despite the fact that the population follows a distribution that's not normal, that's skewed, because our sample size is large, 100 homes, the distribution of the sample means will follow a normal model. And hopefully we've shown you some of that with some simulations in class. So with the sample size of 100, the sample mean will follow an approximate normal model. So that's the first thing. Before we can draw and label this, we need to know, if we're using a normal model, where the center is going to be and what the standard deviation is going to be. So we'll list those. The mean of the sample means will be the same as the mean of the population, which was 224,000. But the standard deviation, when we look at samples of 100 homes, the standard deviation of the sample mean will not be as spread out as the standard deviation of individual homes. So we'll take the standard deviation of those individual homes and divide by the square root of our sample size. And so the sample means will have a standard deviation of only 6,500. And then we could draw this. So this time, these are average assessed values for groups of 100 homes. We'll still be centered at 224,000. So put a K there. And now if I go up one standard deviation, I'm going to go up $6,500. Just for room's sake, I'm going to write it down here. I'll be at 230,500. If I go up a second standard deviation, I'm at 237,000. And if I go up a third standard deviation, I'm at 243,500. And we'll do the same thing the other way. And I'm just sort of staggering those numbers just so you can still read them, but this is one standard deviation below. Here's two standard deviations below, and here would be 3. We drew the model label. We could even put those percentages in here that 68% of the time when we look at groups of 100 homes, we would expect their average assessed value to fall within this range. 95% of the time within 2 standard deviations, and 99.7% within 3. So original, just assessed values for all homes was skewed, but once we start looking at samples of 100 homes, the average assessed value of groups of 100 homes would follow a normal distribution. centered here and would have a much smaller standard deviation than our original data did. So that's part A. Let's look at what we're going to do in part B. All right, comment on the population of homes and their assessed values. If local officials find the assessed value in the sample to be only 204,000. So if I keep my picture up here for a second, look and see where that is. If you were to get a sample of 100 homes that only has an assessed value of 204,000, that's more than 1, 2, 3. That's even more than 3 standard deviations below the mean. Let's investigate that a little bit further. We could even say how many standard deviations that is away from the mean, right? If you want to know how many standard deviations an observation is away from the mean, that should sort of ring a bell, and there should be a word right on the tip of your tongue. Hopefully it's z-score. So let's compute the z-score for a sample like this. If we take 204,000, see how far away that is from the mean, and then express that in standard deviations, you get, and make sure your answer is reasonable, right? If I get an answer of negative 2.1, I look at my graph and I go, well, that's not right, right? I know a reasonable answer here, it must be negative 3 point something. So here we get negative 3.08. So to get a sample like that is more than 3 standard deviations below the mean. Those values would be incredibly rare. This is probably leading to, hey, maybe this model's not the right model, right? This is assessment values. You probably, if you live in Cecil County anyway, you probably get information on the assessed value of your house every 3 years or so, and those change. Sometimes the assessed values go up, sometimes depending on the market they go down. It seems to me that perhaps this whole model is centered a bit too high. Maybe it should be centered down a little bit, given how unusual it would be to get a sample mean like this one. So what else can I write about this here? So this sample, is more than 3 standard deviations below the mean. And then we could even say that this indicates perhaps that this assessment model would need to be updated here. We like it when assessed values go up, but that doesn't always happen. There are time periods where they go down. So this could be an indication that we're at one of those time periods here that that's happening, given how unusual it would be to get this sample. All right, let's look at one more. Erase this. This one's completely new from what we just looked at. Okay, second example. There are 33 students in an intro stat course over at the university. From the professor's experience, exams take an average of 5 minutes to grade, with a standard deviation of 5 minutes. Grading time per exam is not normal. We don't know what the shape is, but it's not normal. The professor starts grading at 7 p.m., wants to be finished by 11 p.m., get a good night's sleep. That means he needs to finish grading in how many hours? So this is the really hard part of this problem. How many hours from 7 p.m. to 11 p.m.? So until 8, 9, 10, 11, 4 hours. How many minutes is that? If you take 4 times 60 minutes, that's 240 minutes. So he's got 240 minutes to get this job done. To finish grading in the allotted time, what will he need his average grading time to be per exam? And we're going to stick with minutes here. So he's got 240 minutes to get this job done. And let's think about how many exams he has to grade. He has 33 exams to grade. if we divide, this will give us how many minutes he can spend per exam. So if you do this, he's got about 7.27 minutes per exam. If he'd like to get to sleep by 11 there. All right, part C. This is a problem about the distribution of the average grading time. Not how long it takes to grade an individual exam, but on average how long it takes to grade this group of 33 exams. Since it's 33 exams, the sample size does exceed 30, and so even though the distribution of individual grading times didn't follow a normal distribution, the normal model will apply since our sample size is over 30 here, is sort of a larger sample. Since we're going to use the normal model for average grading time, we need the mean and the standard deviation to do that. So the mean will be the same as the mean of the population, or 5 minutes. But the standard deviation here will be smaller. It'll be the standard deviation for those individual exams divided by the square root of our sample size. So we'll take 5, that's the standard deviation. We have a sample size of 33. So the standard deviation for the sample mean will be 0.87. And now we can use this along with the fact that these average times are going to follow a normal model, and we can do some problems with that. I think just one more part. So what's the chance that he finishes by 11 o'clock? So determine the chance he finishes by 11 o'clock by determining the probability that the average grading time is less than 7.27 minutes per exam. So let's draw a picture, and we'll use these. So we just said that we're looking at the average grading time for 33 exams. It follows a normal model centered at 5 minutes. And if he wants to get to bed on time, he's got to finish, and he has to average less than 7.27 minutes. So we want this area less here. So this is sort of, our target for Y bar. And by now you should know how to do this. Pause the video, make sure you can get this number. Unpause it and check back. Hopefully you opened up StatCrunch, you looked at the normal calculator, you put in a mean of 5, a standard deviation of 0.87 that we just computed. And if you did that from StatCrunch, this area is about 0.995. So that's good news for the professor. There's a 99.5% chance that he's going to average 7.27 minutes or under per exam, which means he gets to go to bed by 11 o'clock. It's finished by 11. Go to bed or watch late night TV or whatever we want to do at that hour there. Okay, so that's the end of this one. So this one had 2 nice examples on the distribution of the sample mean. That's it.